Okay, so from the sublime to the ridiculous, I guess. So now we're going to talk about imperative programming. And in particular, I'm going to talk about algol. Okay, and this is the subject of my lectures. And it reminds me of a discussion I had last night. So some of you at least have heard the word algol, besides the fact that it's a star, as a programming language that goes back to 1960. So it was quite some time ago, however many years that is, getting close to 60 years ago, right? 55 years ago. So I was reminded when I'm thinking about preparing my lecture, I'm sure that many of you are asking, what the hell does that have to do with anything? And it reminded me of a semi-drunken discussion at the bar last night in which I was lamenting the fact that somehow in computer science, anything that's old is automatically wrong. So it's like, oh, you know, Newton's laws are like, what, 300-400 years old? Can't we have like version 2, for Christ's sake? I mean, of what use can they be? They're old. It's old. Forget it. Okay, it's no use. It's a very strange thing, and so people spend all sorts of time making the same errors all over again just for the sake of being new. So the interesting thing about algol is there's a saying, which was, I won't write it here, but there's an old saying about algol is that it's a considerable improvement on most of its successors, and that is very true. So what I'm going to do is I'm going to talk about algol, I would say, via Reynolds. It was Reynolds. I must admit, when I first met Reynolds, I thought he has this weird obsession with algol, and I'm like, what the hell is that all about? And I realized over time that, as usual, John Reynolds was right. So Reynolds did something called idealized algol, and I'm doing my own version, which is called modernized algol. And I called it that because it rhymes with Reynolds' version, which is called idealized algol. And this brings up a little bit of a story because one of my first drafts of the book, I called it Idealized Algol, and I asked John to review the chapter, and he went ballistic because there was a particular thing which I'll explain to you that I don't do that he does, and he absolutely could not abide that. So I thought, oh God, now I can't call it. I wanted to call it Idealized Algol in homage to him. So I had the idea, I'll call it Modernized Algol because it rhymes. And that way everyone knows that I'm really saying Idealized Algol, but that's not Idealized Algol because it isn't exactly what Reynolds said. I'll say that straight away. Okay, so what I'm going to do is I'm going to talk about my own version, which I mainly, in my mind, attribute to Reynolds, but I'll tell you it's not exactly. John does not approve of what I'm doing. Okay, so I know that, but okay. In any case, so I call it Modernized Algol, or MA. And the main message that I want to get across, that I will explain in the course of my lectures, is that Haskell is a dialect of Algol. Okay? Yes. This is true, okay? This is true, okay? This is very true. And so I'm going to explain to you how this comes about, and in the process I'm going to debunk some stuff that is said that isn't true. Okay, so I'll explain that as I go along. So this is my main message. So the overall, okay, the main point that you should take away from this in some way is that there's a way of thinking about imperative programming that combines it with functional programming in a very elegant way, and they did it in 1960. Okay, that's like totally astonishing. Okay, it's a really amazing thing. So it was a higher order programming language, okay, with certain limitations that it had because it was 1960. But when you see what they were on about, what they did, it was incredibly beautiful and prescient. Okay, so I'll explain that. So here's my idea. So what is modernized algol? It's basically PCF with a modality. And I'm going to insist on this, okay, this terminology, okay? The issue is the modality, and I'll explain something that sounds a little bit like that in a minute and how to put that in context, because there's a giant amount of heavy weather made about the thing that doesn't matter. Okay, so I'll show you how this goes. So it's a PCF with a modality that distinguishes expressions from commands. Okay, that's the idea. So what I'm going to do is, in this language, I'm going to start out, I'm going to have a type system that looks like PCF, and I'm going to add something here. But the thing I'm going to add is secondary, which is why I don't why I don't write it down now. Okay, because I want to get, one of the things I want to get across is an order of priority of ideas that has been inverted in the popularizations. Okay, so that's what I would like to rectify. Okay, so we have the notion of expressions, and the expressions are exactly like they are in PCF. And there's going to be one more form of expression which is related to what I'm going to fill in here, but we'll get back to that later because I want to emphasize the point that that's secondary to what is primary. So these are the expressions. And then these are the commands, which I write M, okay? That's the way I did it, okay? And the idea about the commands are these is where you do the imperative programming. This structure is present in ALGOL, okay? This is nothing special about any more modern language that seems to have invented it, okay? The idea is you have higher order functional programming, okay? That's the beautiful thing about ALGOL. And as a matter of fact, although it's not necessary and I won't do it, it was even call by name, because that weird term call by name whose origin I don't understand, that term got invented for ALGOL, okay? So it's like before your parents were born, for God's sake, okay? This is like a long time ago, okay? So, and what are the forms of command? The forms of command are the imperative programming, okay? Now, I'm tempted to write here what ALGOL actually had, and this is also what idealized ALGOL has, and I'm going to depart from that. What ALGOL actually had was composition of commands. I'm going to get that as a derived form, okay? But you could imagine it like easy enough thing to do. So I'll fill in, I'm going to have a derived form there. And it had a way of declaring what I will call assignables, okay? So the idea is you have a declare, I write A, E, X dot M, and typically in concrete syntax I'll say declare A initialized to E in M. That's what I will usually write. And then it has a notion of set A with E and get A. So these are imperative programming looking things. So you could write this, A becomes E, and you could I write it in the book add A, for lack of a better, more imaginative way to write it, okay? And the idea is that the A's here, are what I call, this is a neologism that I invented, as far as I know anyway, which are, I think I did, I didn't get it from somebody else, but maybe somebody else used it and I don't know about it. Okay, A's are what are called assignables. Assignables are not variables. So in ALGOL they call them variables. These are not variables. They do not behave like mathematical variables. They are not variables. So I will insist on this point. Okay. Now, okay, that's the setup. And the question is, what goes here? So the point that I want to get across, and we'll see how this goes in a moment, is set and also get are forms of command because they depend on the state. They depend on what the contents of the assignables are. Okay. So everything to do with that has to do with the memory. And then if you look in the book there, I have versions of like concurrent ALGOL and distributed ALGOL for doing distributed programming stuff. The details differ, but let's say we're doing basic imperative programming. So this is supposed to represent a memory, and these are locations in memory. Locations in memory are not variables. I have to emphasize that. Now, the idea is that, as you'll see in a minute when I write down the statics and dynamics, get is a form of a command. Now, in original ALGOL, commands merely had an effect. They didn't have a value. Okay, that's the idea. Well, and in fact, all you had was return. I don't remember what syntax they used, but the gist is you just had return as a base case. Commands did not have values. Okay, so what we do here is the generalization, this is in what I have in modernized ALGOL, is that I have the execution of a command can return a value, and that value is passed to the next guy in line. Okay? Now, the interesting thing is now I have to fill in what I'm going to get here. Because the constructs I'm going to give are associated are the introduction and elimination forms for a type constructor called command of tau. So this is the thing I'm going to have here. And I'm going to have a way of encapsulating a command and forming a value. And then the analog of semicolon is something I call bind or BND, which takes an expression as its first argument and binds a variable, an actual variable. Okay, this is a mathematical variable, okay, for use in a command. And from this, we can get idioms like that. So you'll notice that when I write down I'm trying to emphasize the type structure, and the type structure I want to emphasize is that of a lax modality. Okay, that's what I'm doing here. It comes from, it's the structure of a lax modality. So I don't have time to talk about modal logic and how that all works, but that's the issue that I want to have here. I want to have different forms of phrases, which are expressions which you could call pure in some way because they don't depend on memory. Okay, and you could call these impure, whatever you like. Okay, and these could be called impure maybe if you want to be pejorative, and they depend on memory. Okay? Okay, so that's what we have here. So the first thing that I want to mention that's important is that I have a modal distinction between expressions and commands. Okay? Expressions of type command are not commands. That is what is extremely important here. Okay? All right, so we'll get to this. Everything is very carefully orchestrated. Oh, what I started to say is, because I'm very attentive to the type structure and the connections with modal logic, the syntax is a little awkward to program in, but immediately you can write down derived forms, and then it becomes very familiar. So, so bear with me, like on the certain ways in which things, it seems a little stiff, and that's because I want to get the type structure down exactly right. Okay. So I have to write the statics and dynamics. But the idea is that E should have the type command tau, which is the type of encapsulated commands. So the values of that type are of this form. They're expressions, which are values, which are frozen commands, if you will, that haven't been run yet. And what this bind does is it runs the encapsulated command, gets its return value, and then passes it to M inside another command. Okay? That's what's important. Okay. So that's the setup. So that's what the structure of the programming language looks like. Now let me mention the distinction that I mentioned earlier about idealized algol and modernized algol. Reynolds, unaccountably in my mind, preferred the following setup, which was also true of algol. Okay, which is you do not have get as a form of command, but instead you have an assignable as a form of expression. And you call it a variable just to be annoying, okay? So you write that down and you have an assignable as a form of expression. If you do that, then no command need ever return a value, because the only command in this little language that returns a meaningful value is get. Set, you can consider it returns a unit, so who cares about that? Inductively, this will return unit, so the whole thing will return unit, and then you just have a blank return like you would have in C or something like that. Okay, so the reason for having command of tau as opposed to just command, so Reynolds just has a type called command. Okay, Reynolds did this in the 70s, long before other things got popular. He had all of the ideas already. Okay, so and I'm just showing you an elaborate version of these things. Okay, so that's the difference. I'm not going to do this. There are many reasons why I don't want to do this. Okay. But just to give you a little bit of an example is if you do that, it does violence to all kinds of things. But one of the biggest, most practical-minded issues is it plays hell with concurrency. The reason is if you allow myself to use an assignable and I write an expression like that, the concurrently executing threads get 2 bites at the apple here to interfere with A. And so there's no sense in which this is equal to 2 times A, just to say the least, because of concurrency, if they're assignables. If they're variables, of course, x plus x is equal to 2x, and it always will be, and that will never ever change. But if you try to pretend that assignables are variables, it's a bad idea anyway, conceptually, but when you have concurrency, you are screwed. It's completely awful. Okay? It's completely awful. So I consider it to be a historic mistake. Okay? That's just my own view. What I'm presenting is perfectly workable, and you can decide whether you like it or you don't like it, but that's why I'm doing this. There's a reason for all of this. Okay? So there's a huge messes are made out of issues like that. It's like, oh, God. Okay, so anyway, if you just do things properly, I think a lot of things work out more smoothly. Okay, so in particular, Dan later on is going to be talking about parallelism, and parallelism fits perfectly nicely at the expression level and doesn't involve any issues of concurrency. So one of the things you're going to learn this afternoon, if you don't already know it, is despite common opinion, parallelism has zero to do with concurrency, nothing, zero, unrelated, okay? And Dan is going to teach you about that later on today. Okay, so I have reasons for doing this. All right, so let me write down the statics so that I can make another remark about the structure of the language that I'm writing down. Okay, so good. So let's look at the statics, and I'll try to be brief because by now you're getting familiar with all the tools, so I'll be very brief, okay? So what we have is a judgment for expressions, which is parameterized by the types of the assignables. So it's a sort of a context, but for the assignables. All right, and I call that a signature. So I write that as A1 twiddle tau 1, da 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 da, AN twiddle tau n. Why do I use a twiddle? Because I bloody well do not want to use a colon. Because an assignable is not a form of an expression of its type. An assignable is a location in memory whose contents has a type. So if you write A colon tau 1, you're implying A colon tau, you're implying that the assignable has that type, which it does not do. Okay? So that's why I insist on that notation. Okay, good. So that's for expressions. And then I have a separate one for commands. Okay, which I write with a wavy thing through the colon. Who knows why? It was the best I could come up with. Okay, so I want to have a different judgment, okay, which looks like that. So this means it's a well-formed command whose return value is of type tau. Okay, that's the idea. Okay, so now let's write down what these things are. I'll just sort of cut to the chase to get to the main important points. If I have a command that returns a value of type tau, then that thing can be freeze-dried and encapsulated and turned into an expression whose type is command of tau. Okay, otherwise, let me just check my thinking. Yes, otherwise it's PCF. Okay, it's just PCF. All right, so that's good. All right, oh, by the way, an advantage, one of the problems of idealized algol and one of the problems of algol is for the whole language to work properly, it had to have call by name. And you just know that can't be a good idea, okay? And the reason is they don't have the ability to make the distinction. They have to have it's a little technical that I can't do with the board, but by having encapsulated commands as values, you don't have to depend on call by name anymore. Okay, thank God. So get rid of all that, okay? All right, so that's the reason I'm doing this, okay, as I do it like that. So yes, I believe there's no other distinctive form of expression. Everything else is PCF. In particular, you have fix, which we'll use in a little bit, and and other things. Okay, good. So what are the rules for the commands? So the rules for the commands say, if I have an expression of type tau, then the command that returns E is a command that returns, lo and behold, a value of type tau. So I can write it like that. And so now, by the way, this is the intro form for command. So this is command intro. And now I'll do command elim over here. Command elim is a form of command. So the idea is that if I have an expression whose type is command of tau, then, yes, that's one thing. And the second thing is, assuming I have an x of type tau, which is a variable, by God, then if I then compute with that guy and get something of let's call that tau prime, and for the sake of symmetry, let's call that m prime, then I will get the following thing, that bind, which eliminates from the type tau, binds a variable x in m prime, and that will be a command that when executed will yield the tau prime. So this is the bare infrastructure of commands, okay? This is the bare infrastructure of the lax modality and modal logic. That's where this comes from, okay? So that's what the setup is there. So now let's talk about the things that are distinctive to assignment, that are distinctive to having assignables, okay? So one is the declaration, okay? So if I'm going to declare, let's write it, I'll write it in the abstract syntax. So I'll write it like that. This is a command, oh, I left something out, E, okay. And let's write x dot m prime again, just for symmetry. So this is a command of that type under the following circumstances. If E is an expression of type tau, and if I augment and say, oh, here's an assignable, and that assignable A has, oh, I'm sorry, what should happen is I wrote something wrong earlier. I knew something didn't feel right. Okay, I wrote something wrong earlier. The assignable A is bound within M. This is what I want. I wrote that wrong earlier. I was thinking of something else. Okay. Excuse me for my mistake. Okay. So it's E and A dot M. The idea is the assignable is a symbol which is bound within M. Okay. It's not a variable. It's just a symbol. Okay. Sorry about that. I made a mistake. Okay. So, and in the presence of A, I have a command of type tau prime, then the whole thing is of type tau prime. So what I'm doing is I'm declaring an assignable. I'm saying declare A, initialize it to E, and execute the command M prime. Okay. We're going to get a little bit later to the topic of references. This has nothing to do with references, and I'm actually going to argue that references have nothing to do with state, okay, which is, you may find surprising, but it turns out to be the case. So, okay, so I will do that. So that's the declare. What does the get look like? Well, if I have a get of A, I write it like that, and I'll explain why in a minute. That's a command of type tau, oh, in a situation where A is of type tau. So that's simple. So it's an atomic command of type tau. And then finally the set, you can figure out what that would be. If I have an expression of type tau, and I'm in a situation where I have an assignable of type tau, then I can set it. Whoops. Sigma A tau. I can set A, E, and that's of type tau. That's a command of type tau. And that's it. That's my syntax. That's the entire syntax. Okay? So, good. I'll give you the dynamics momentarily. You can halfway guess what it's going to be, but you can see what the statics is. So let me make sure that I have said everything I need to say. Okay, yes. The one important point I want to make is that the way I think about this is that what are assignables? Okay, what are they really? This is the way I think about it. The assignables are indices to families of get and set operations. So the idea is that at any time you have a bunch of assignables, A1, tau 1, AN, tau n, that's my sigma. In the presence of those declarations, I automatically have available to me the getter for A1 and the setter for A1, and so on, all the way through. A is not a value, it is not an argument, it is not evaluated. It's just the index. I could write this as get sub A, okay, if you want, and set sub A. It's the getter and setter associated with that assignable. Another term for this is these form what is called the capability to get and set A. Those are called capabilities, okay? in the OS literature, there's a lot of ooga booga made about capabilities, about being magic numbers and blah, 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 blah. They're just procedures, that's all, period. That's all they are. Nothing else, okay? So this is the capability to get A, this is the capability to set A. If I pair up the getter and setter for a given A, what have I got? I've got a reference to type A. So I can define ampersand A to be the pair get A, set A. Why? Because a reference to A is the thing that gives you access to the capability of getting and setting A. That's the whole point. Okay? There's nothing. Okay? So I'll stop there. I'll come back to this in a minute because there's a fallacy out there that says references have something to do with heaps and heap allocation and garbage collection. That's false. Okay? So I'll show you how this works. Okay? In a perfectly civilized way. Okay, there's going to be an additional premise on this rule. There's going to be two additional premises that I'm going to have to fill in here and here as soon as I get to the dynamics. So I'll fill them in because I want to motivate them by giving you the dynamics. Okay, so just mark that, there's going to be. Okay, so now I will mention something as an aside. Okay? So it's a common idea, I will write this down, the notion of a premonad, okay, all right, which is a type constructor A, and we'll have a mapping from A to T of A, and we'll have a mapping from T of A to T of B to T of B. Let's say I'll define that, okay, this is it. So I have a type. It's a family of types indexed by types, equipped with these two operations, okay? And I'm going to insist, it's often called a monad, but that's a lie, okay? Because to be a monad, you have to satisfy equational laws, and in well-known programming languages, they do not satisfy those equational laws. They are not monads, that's a lie, okay? It's a premonad, okay? So the exercise I will give you is show that, well, every damn thing in sight that you can think of can be given the structure of a premonad. In particular, I can give that you can define R and B for T of A being command of A. Okay? It's trivial. Just do it. Okay? The fact that command of A forms a premonad is of no importance whatsoever. It has nothing to do with anything. The fact that you can write down, if you have something of this signature, does not give you effects. If, on the other hand, you start with the modal distinction and you have a notion of effects that you build into the language by having a level of commands and a level of expressions, you can structure those so that they form a premonad. Big deal. You can structure lists so that they form a premonad. You can structure any damn thing so that it forms a premonad. The requirements are trivial. You just have to have these operations. That's it, and you're going. So my point is, effects have nothing to do with premonads. The fact that you have a premonad has nothing to do with it. If you have effects, you can structure them to form a premonad in the way that I'm sketching. So what? Okay? The important thing is that you start with the notion of effects. So you start with the modal distinction. You start with the modality. And then the modal distinction that I have here. And then, of course, that can be turned into forming a premonad. Because it's the lax modality forms a premonad. That's what's happening here. It's the lax modality that gives rise to the effects. It's not the fact that some signature can be implemented in a particular way, okay? So the order of priority somehow gets inverted, okay? And so I want to mention this because, you see, Algol had this right in the beginning. And, okay, that's the first point. So you can look at that, so that's a little exercise, you can do that. Okay, so now back to the chase. What does the dynamics look like? And then I have to modify the statics. or not. So I'll explain that. So there's two missing things up there, which I'll show you. But first, let me write down the dynamics. So what does the dynamics look like? A is a value relative to sigma. E is a value, sorry, what did I say? E is a value relative to sigma. E transitions relative to sigma to E prime. So the idea is that the expressions can know about assignables. For example, if I have an expression, command of get brackets A, if I expect that to have, let's say, some type like command of nat, I at least have to know that A contains a nat. If I don't know that, I can't make this judgment. So the expressions do care, because I'm going to assume that this is well formed in that, with that signature, and then the preservation will tell me it's like that. So the expressions do care about the domain of the store, if you want to say that, the active assignables. They don't care about the contents. Okay, so that's a critically important thing. And now there are going to be two choices, but I'm going to do, first of all, the classic algol dynamic semantics, and then I'm going to relax it. Okay? So the classic algol dynamic semantics looks like this. The important thing is here. What we write is we have what I write as a memory, written like that, M, making a transition relative to sigma to mu prime M prime. Okay? And then the corresponding thing to being a value is that this is a final state with respect to sigma. Okay? So the thing I want you to notice is if you're not familiar with operational semantics techniques, then I want to emphasize this point for those of you who aren't. What's really elegant is the way in which, as we'll see how it all emerges, is that I have a family of transition systems indexed by sigma. The memory can change, but but we have one set of assignables that governs both sides. Let's see how that plays out, and then you'll understand what I'm getting at in a minute. So it's nice, because there's going to be a different way of giving the dynamics, okay, which has different properties and is not algol. But let's do the algol dynamics first of all. Okay, so we do the algol dynamics first of all. So what are we going to do here? So first of all, we can get this out of the way. Besides PCF, the only thing I care about is that command of M is a value in sigma, and implicitly I'm considering this for the case that M is a command that makes sense over sigma. Okay, so that's what I'm doing. Okay, otherwise the expressions don't change. Oh, by the way, yeah, I don't have time to write it all on the board, but you can look in the book. You'll notice that I don't have anything like an if statement, an if command. I don't have a while command. I don't have a for command. I don't have procedures. I don't have anything like that, because they're all neatly definable in the mechanisms that we already have at hand. Okay? It's in the book. I don't have time to go into it. Now, if you wanted to define a while command, for example, you'll use fix, because while is self-referential. A while is an if that when you get to the branch of the if, you go back and become the while again. Okay? So it's a fix. So that's all very clean and elegant. It's a nice thing. You don't have to come up with these things. They kind of fall out for free, at least at the level of the semantics. We can talk about convenient notation. That's a separate issue, but just at the level of the semantics. Okay, so I don't need to talk about any such things. All I have is what I have here. So here's the only value, apart from the PCF stuff, here's the only value we have. So the interest lies in how we execute commands. So some of it is pretty straightforward. So for example, if I do this, then in any memory, the return command with E, with sigma, will evolve in place by simplifying this expression. And if that expression achieves a value, then this state is final. There's nothing more to do. You're returning 7, then, well, that's it. You're returning 7. Okay, that's the whole shebang. So that's return. How do we do bind? Okay, bind is a little more complicated than you might think at first, because, well, I have a memory around, but these guys won't really depend on the memory, but I'll write it down. So bind x dot m, yes, okay. And I will say this makes a transition to leaving the memory alone and bind E prime x dot m. I think I need a new pen. So let me do that. Okay, if exactly when you think. So the point is, in this setup, evaluation determines what command comes before another command. You evaluate that as an expression. Now, oh, and by the way, as a matter of notation. So the notation here is designed to connect with concurrency. I won't have time in these lectures to talk about concurrency, but my idea is this. What I really have is a concurrent composition of the main program M running as simultaneously with threads that govern the contents of each of the locations. Every assignable is a process, and you contact that process to ask it what is its contents or to set its contents. So we do it entirely in terms of concurrency. That's what eventually happens here. That's why I use this notation. So a little bit later in the book, that's all developed in full. Okay? So that's what's going on here. Okay. Now back to the chase here. So what do I want to do is I now want to execute. I've evaluated the argument, E. So by a canonical forms lemma that I haven't proved, but it should be clear, the value of E, if it's well typed, must be an encapsulated command. Let's call that M. So let's consistently call that M prime or something. So I have command M, and we have X M prime, okay? And now the question is, what do I do? Okay, how do I execute this guy? Well, here's what you do. It's kind of slick, okay? Can you think about what we would do? What would we do here? Well, we kind of want to start executing this command, and when it's done, we want to pass its value to here. But in this structural operational semantics, how do I do that? Well, the beauty is I go above the line, you see. I go up above the line, and I say, take a step on M, okay, and get back a modified memory, because I haven't written those out yet, but we will be able to modify the memory. And we'll get a modified command, and then we reconstruct the world by saying, you're now going to resume command M prime. Oh boy, that was a bad idea. Oh my God. All right, let's, I don't know what to do here. Let's call this M1 for lack of imagination. Otherwise, see, I got myself into trouble. That was stupid. Okay, so then we'll write x.m1 and go my parens match, yes, and that's what I do. It just occurs to me as I write this, probably not, but have any of you ever heard of PC losering? No. You've heard of PC losering? Yes. We're PC losering, that's what's going on. Okay. I'll explain to you offline about PC losering. It's a really cool idea from the old days of computing that is like, has to do with interruptible system calls. Okay? Can you see why this is PC losering? No, but it is. Okay? All right? Taking the syscall to execute M, it's sort of getting interrupted, and I'm modifying the user state to update what the M is it thinks it had there. Okay? And then we resume from there and do the syscall again. Okay? It's PC losering. Okay. All right. Oh, well. That tickled me anyway. All right. So, okay, now we do this. Now, suppose I have a command, okay, which is a return of E. I keep executing that command. I keep reconstructing the situation. Okay. Now this is a return of E where E is a value. We've got that done because we kept working on M, and we're doing all sorts of things. So in particular, it might be a return. So I evaluate its argument, and now I get to command of return of E and x.m1, okay? Then what do we do here? We leave the memory alone, and we resume execution by plugging E for x in M1. See, one of the things I dearly love about this field is all sorts of like hacky sounding things have very systematic treatment and come up in an elegant way. in the semantics. The semantics talks about everything. There's nothing is missed. Okay, everything is there. It's all you need to know. Okay? So all right. Anyway, so there's that. So now, what do I do about set and get? Let's do those because they're easier to write down first of all. So if I have a situation, so the notation I use is something like that. A contains E, which is going to be a value. And I'm executing a get of A. And I'm executing it in a situation where I have A is available. Then what do I do? Well, the memory stays by itself. And then I return that value. Oh, yeah, very nice. I've preserved the invariant. This is a command, that's a command. Okay, so it works out very elegantly. Okay, I'll leave set as an exercise. Okay, you can look it up or you can do it yourself, but in the interest of time, exercises do set. Okay, so it looks a little bit like that. The one that's tricky is also an example of PC losering, okay, which is I want to do a declare. So I want to do declare E, A dot M. Okay, in order for the sake of expediency, let's assume we've already evaluated E because it becomes, I have to write some rules to do that. So let's say we've already evaluated E so that I can get to the interesting part. Okay, then what do? I've already evaluated E, and now here comes the interesting part. Okay, so the idea is, and now here's the point, what is called stack allocation or the stack discipline. Okay. This was the idea that was invented by Dijkstra. Okay. And in fact, oh yeah, I forgot to, I'll mention in a minute what stacks have to do with recursion in a moment, because that was an idea invented by Dijkstra, who got it right in the first instance. Okay, so the idea is this. So we're executing this declaration. Now here's the point. I want to express the idea that assignables in ALGOL, I'm going to relax this in a moment, but I want to express the idea that assignables in ALGOL are stack allocated. That is, when I declare an assignable A for use in M prime, I can get it and set it in M prime. When M prime is finished, it's deallocated. Okay, that's what I want to get across. All right, but I don't want to deal with dirty things like stacks. Okay, that's a terrible way to think about things. Okay, so here's what we do. What happens is, well, you can think of it as in the following way. I've got a value which is the initializer for this assignable, and I want to execute M in the presence of that assignable. So what can I do? What I do is I go above the line and say, let's extend the memory with A having the contents E, and I execute M. If I can, I execute M, and I will, in the process of doing that, maybe modify some outer assignables, maybe modify some inner assignables, and get a new command. The declared assignable, some outer assignables, the declared assignable, and a new command. And then what do? Again, it's an example of PC losering. What I do is I say, update the memory, and they declare the E stays the same because I'm considering the case where that's a value. So I reset the world, and I write it like this. So think about this. This is incredibly slick. Okay? So because the idea is I reconstruct oh, no, this should say E prime. I knew I made a mistake. Okay, that should say E prime. What I do is I take your starting state in which you declare A to be initialized to E and you execute M. Once you've taken a step of execution on M in that situation, you might have done a set and updated that to E prime. So the resulting state is I restart your program in a situation in which the initializer is not what it was, but what it became as a result of your execution step, and then proceed from there. Ooh, this is extremely slick. If you don't get it right away, that's all right. Study it offline because this is I love this. This is the most amazing thing, okay? This is a really nifty thing. So the idea is that the notion of the stack discipline is going above the line, doing a step, and then reconstructing the world below the line. That's where the stack is. Okay? Yes. Did I make a mistake? Could be.
Shouldn't you have faced with the context for
I'm not able to hear you.
Shouldn't you update the context for assignable above the line?
Oh, sorry. Yes, he's right. You're absolutely right. This should then put in tau, and really I need a parameter tau on here to know what the type of the assignable is. If you look in the commentary, I mentioned why I do this. Okay, so you can look at that. Okay, so that's the slick thing. And then how do I get out of the declaration? And now here comes the important point. Okay, so now suppose I'm in a situation where I'm doing a declare, tau, e is a value, and I have a dot m, but we're no longer able to make a transition. We're in a final state, which means it says red of a prime, e prime, where e prime is a value, okay? And I make the transition. What do I do now? So that if I were to apply this rule, there's nothing to do. Red of e prime, where e prime is a value, is final, okay? There's nothing to do. So this rule doesn't apply. So what do I do in this case? And now this is the tricky part. So what do? I've declared an assignable initialized to e, and I'm returning a value, and I want to, what do I do next? Well, the idea of the stack discipline is when you finish executing the body of the declare, then you get out of it. Okay, so you would write mu, let me make sure I'm right, yep, mu red of e prime. Because you finished executing the body, and now, boom, you return e prime. And you're done. Okay, so that's the dynamics. Are you with me? Okay, now we go through our head and do type safety. Can I get a type safety theorem for this? Is this a well-defined scenario? That is, does this dynamics, of course I omitted a bunch of rules, but does this dynamics match up with the statics according to the principles of progress and preservation, which I mentioned to you on Monday? Good, you know.
Is it possible that we capture
Yeah, I think that's what, I know what you're going to say. So the question is this, okay? What makes you think, so let's look at, suppose we're doing, you're doing your head. This is how you work. Do the preservation proof in your head. Suppose that this is well typed relative to sigma and that the memory matches sigma. So let's not worry about this. So let's say the memory matches sigma, that's a given. All right, this is well typed relative to sigma, right? Now look at the statics rule for declare on the upper left, upper right there in the middle board. Okay, so it means that E has a certain type relative to sigma and that E prime has a certain type relative to sigma extended with A. Yes, that's what it says up there for declare. Notice the M prime, when you type check M prime, you type check it in the extended signature with an additional assignable. That means that E prime gets to refer to A. Okay? Now you're supposed to do the preservation proof. So the preservation proof says if this is well typed in sigma, then this is well typed in sigma. No, it's not obvious. Maybe, but it's not obvious. Because this is type checked, this thing has some type tau prime in sigma extended with A, and you want this thing to have some type tau prime, but in sigma alone. It's not obvious you can do this. So now, let me mention something important. So in ALGOL, you could only return a number. Okay, they had ints and floats. Okay? Because you could only return a number, then you can show that if a number, a numeric value, type checks with an assignable present, it will type check with the assignable absent. In fact, it'll type check without any assignables at all. Provided one thing. What is the one thing that I need? So suppose I have the conjecture. If E is a value of type nat and it type checks in a signature with an assignable A, it will also type check at type nat without A. Is that true? Under what conditions is that true?
Default values?
Someone is speaking, yes?
Default values?
What about values?
Default values for the assignable?
I didn't hear the first words.
Default.
Equal.
Default.
Default.
Yeah.
I'm not sure I understand that response. What does that mean?
When you construct an assignable, it has a default value even if you
No, I don't care about that. What I'm worried about is the return value. When you return a value out of the scope of an assignable, and that value is of type nat, what makes me think I can return it out of the scope of the assignable? I'm deliberately leading you like in a way that you're going to make an assumption that you're not realizing you're making. Okay, so if I have a value of type nat, can I return it out of the scope of the assignable? You might think, yes, right, it's 7, it's 8, whatever it is. Bullshit. Okay, what if the successor is lazy? Oh, right. If the successor is lazy, then the argument of the successor is an unevaluated expression. Yes? You can't export it. You can't export it from the scope. Let me give you an example. Algol only made sense because the constructors for the values are eager. Okay? Ha! You don't think about it. It's like it's easy to go over this. So let's look. In an eager case, if E is nat and E is a value, then it's successor of 0. It will have the property we're considering under question. Okay? What if it's lazy? Can I construct a counterexample? I want to have, this requires a little cleverness, okay? I want successor of something, which is an expression, that uses an assignable A. That is, it appears in the expression. My goal being, I want to make sure it will not type check outside the scope of A. So you might think, well, how the hell can I do that? I mean, I can't write get A here, you know. I can't write just A because we ruled that out. That's not a form of expression. I can't write get A because that's a command, not an expression. And I can't write here command of get A. At least it's an expression, but it's ill-typed. Because the type of this is, you know, nat command, let's say, and that's not the argument of successor. That doesn't work. Okay? So you might ask yourself, oh, maybe any expression I can write here won't involve. No, you think not. What's a good example?
Bind outside.
You do what?
Bind the binders from outside.
Binders from outside. I think I know what you mean, but I want to write down a self-contained thing. Okay, it's kind of what you're saying, I think, but I want to write it self-contained. This is important because this is how you understand the complexities of higher order languages and what gives them their power. Well, shall I give you the answer? All right, I'll give you the answer. Take lambda x 0, like nat, or z, just return 0. It's a constant function, and gratuitously apply it to that command. To type check this, I have to type check that. To type check that, I have to know about A, even though it doesn't matter for the ultimate value. Okay, so now we have a problem. The language is not type safe, as I've written it. The safety of it depends on the natural numbers, the constructors being evaluated eagerly, of course, because I want the natural numbers, okay? I don't want some other thing, okay? So if I want the natural numbers, then here's a perfect example. If I just willy-nilly make things lazy as a matter of doctrine, then this will screw up. It will not work. I just showed you the counterexample. Isn't that funny? It's the interaction between language features. You might think, whatever I do at the PCF level, whatever, who cares? Make it eager, lazy, I don't care. The command level is separate. Wrong. Okay? Not true. The hard part of language design is making it all fit together in a coherent way. And the way people fool you is they show you a little example of something that works very nicely, and then but they omit to put it in a larger context of whatever its implications. So for example, going back to Algol or Fortran, it's not kind of nice to say I have an assignable A and I write A plus A. What the hell? Why not? Okay? Well, yeah, if you just are telling me about the arithmetic formulas, it does look pretty nice. But it's a disaster when you put it in context, okay? So that's the thing. That makes language design hard, and that's why people who want to fool you by showing their beautiful little example, okay? So watch out. All right? Check your wallet always in those situations. Okay, so what do we do? Okay, so what I do is I introduce, so there's a problem here, okay? So one restriction is make natural numbers a success or eager and require that the result type be a natural number. Effectively, that's what they did in algol. You could also be a float, but anyway, right? Something morally equivalent to this. That's possible, but here's a better idea. The better idea is that I demand the result type to be mobile. Okay? There's something else going to go in the other box, but I demand the result type to be mobile. What is a mobile type? Semantically, a type is mobile if the values of that type can be pulled out of the scope of an assignable. So, eager natural numbers are mobile. Pairs of eager natural numbers are mobile. Or, and for that matter, pairs of mobile things are mobile. Sums of mobile things are mobile. Functions are not. Because the body of a function can have embedded within it uses of assignables, even if the ultimate value is just nat. Okay? Even nat or nat cannot be regarded as mobile. Commands cannot be regarded as mobile. I cannot return the command get A. That obviously fails the condition. Okay? So you introduce the notion of a mobile type, and you say that the result type has to be mobile. All right? You got me? Okay. Now the next trick. It's a bit of hacking. Okay? All right? So is that enough? Well, it solves that problem. But is it enough? Is the language type safe if I do that? So let's say I make the restriction that the result type be mobile, where mobile means that I can pull it out of the scope and get rid of that assignable and it's still well typed. Now, am I done? Well, you know, like for meta reasons, we must not be. But at the object level, am I done? No. Why? Suppose I botched my language design and I didn't give you a return statement. I just gave you a plain return. How can you work around that and nevertheless implement a return with a value? You know how to do this? This is a plain hacking problem. So I screwed up my language design. I left off, instead of return B, I just gave you return. And then you're in this weird situation because you want to write a procedure that returns the contents of some assignable, and you say, well, now what am I supposed to do with that? How do I get you the value? How do I get it out? You can still do it. How do you do it? Just like put on your hacker cap. What do you do? Could someone, I don't know who's speaking. Yeah.
Pass in an assignable and modify that?
Yes, I think what you said is this. What you do is, for every command you want to return a value, you associate an assignable for it, and instead of returning that value, you assign to the return assignable for that block of code, and then you return plainly. The convention is the return value will be in that assignable. Ah, right. That will work. Figure it out for yourself. You can do this, okay? It's just a hack. Oh, that must mean that I am not safe, because I'm simulating the thing that causes the problem. So what other restriction do I need? I need the restriction that you cannot store values that are not mobile. And now I claim, and you can see the details in the book, the language is type safe. So you need the notion of mobility. That's important. That's a critical idea. Now the origin of this idea is in the chapter on distributed algol. We came up with this idea when designing a programming language for doing distributed computing. And when you want to communicate with a program at another site, it's a serious question. Is the value I'm sending over there meaningful over there? So we were interested in things like sensors are located at sites. So I better not like somehow send you a value by which you're going to then read the sensor which doesn't exist at your site. So we worked out a type system so I can send you a reference to the sensor. You just can't do anything with it. All you can do is send it back to me and then I'll do that. Okay? Works out very nicely. It's called ML5, and you should have a look at it. But the concept of mobility is more abstract than that, and so I'm using this here. So the critical thing is that. You have to have the mobility restriction. Algol originally had it more or less by default by being eager and returning only numbers, okay? And now, of course, there's no problem, okay? So it worked like kind of by accident-ish, okay, in a certain way. Okay, so that's that much, okay? So how much time should I be willing to take? I started about an hour ago, didn't I? I think so. It was about 10 minutes to 11, I think is when I started. Yeah, 5 minutes to 11. We're definitely late. Okay. So I'll take a bit more time. Okay, so that's lesson number 1. So that's the notion of stack allocation. And it's expressed by using structural operational semantics in this way. And this idea of stack allocation is something that this not in this form, but the compiler to do it was done by Dijkstra in 1960. Okay, good. All right. So let me go on to the next thing, which I've already mentioned before, which is the idea of references and what I call free assignables. So what I've done so far, so I'll make an interlude about references, and then I'll talk about free assignables. Okay. So the idea is that in the basic form of MA, okay, we have what are called scoped assignables, meaning that the mutable storage behaves in a scoped manner, and we use the mobility restriction as I defined it verbally to you to ensure that that makes sense. Okay? So as an interlude, I want to revisit what I said earlier about references. Okay? References. Okay, I want to have the type ref of tau. Okay, this is what I want to do. That's a form of expression. Okay, so it's a simple point that I want to make, and really I've already made it. Just because the assignables are allocated in a scoped manner does not mean you cannot have references to them. There's lots and lots and lots of papers that, like, when they talk about references, are automatically talking about what I'll call free assignables or scope-free assignables. Okay? They're not coupled. You can have references to them. So the reason, as I mentioned before, I can do the concrete representation. So concretely, I can just define ref tau. I can just define that to be a product, which is give me a moment here. Yes, it's a 1 arrow command of tau. So it's just a command of tau. Command of tau cross tau arrow command of tau. This is the getter, and this is the setter. And in doing that, okay, then I can define the intro and a limb for ref of tau. I can define getRef in the following manner. I'll just give the dynamics, okay? GetRef, if you give me a ref, what is a ref? It's going to be a pair. I'll write a G and S like that. Transitions to the getter. And if I do a setRef, and you give it the pair G and S, it just transitions to the setter. Okay? That's it. Now you have references. As long as this is not mobile, okay, as long as it's not mobile, the whole language perfectly hangs together, and I can pass around references. What is the point of a reference? Why have a reference? Why did references get introduced into a programming language? It's one of my weird questions that might be hard to get my angle why I'm asking this question. Okay? The answer reveals my angle. You should ask yourself, what is the point of references? Why do people have that? So, like, you just learned it, like, well, they told you that, whatever. But no, why do you invent it? What is the key idea? The key idea is that you want, yes, good.
So you can abstract general operations on a state?
Good. That's certainly, that's correct. I have another way of saying it. It allows you to affect assignables that you cannot name. That's the important point. You see, the getters and setters you get in the language, you have to be able to name the assignable to get and set them. You've got to be in their scope. With references, I can do things like have a procedure, that's what you're saying, have a procedure that takes in a reference, then declare an assignable, then call that procedure with a reference to that assignable. That procedure cannot name that assignable. It's not in its scope, but it can affect it anyway because of the references. That's the point of references. Okay? It's not about memory. It's not about blah, 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 about compiler stuff. The point is you can influence an assignable that you cannot name. That's the critical idea. So this is what this does for you. I package up the getter and the setter, and then I give it to you. Now, what's the weakness of this concrete representation of assignable? What's the weakness? There's a weakness. If I were writing some code and we decided to do this, you could criticize it a little bit. And can you tell me why? It's not like the best idea. It would be fine if I had abstract types in play, and then I could do a better job. So one answer is do it with abstract types. But given that I don't have well, I'm going to do it with abstract types, but can you tell me what the weakness is? If you look at the type of ref tau, it just says you've got a getter and a setter. Nothing says that they have to be the getter and setter for the same assignable. So you could screw them up. You could have the getter for A paired with the setter for B, and you wouldn't know the difference. Okay? So then it's not really the right idea. It works, but it's not really the right idea. Okay? So this would be an example of what I would call that's not very good code. Okay? This person wasn't thinking. Okay, so what do? You do it abstractly. And here's the fun part. So abstractly, you just have ref tau as abstract. What is the intro form? The intro is just ampersand A, a reference to the assignable A. You just write it like that. Officially in the syntax, it's ref brackets A, but whatever. Write it ampersand A. And what are the elims? The elims, I'll just get to the main point. Here's the fun part. When you do a get ref on ampersand A, you transition to the getter for A. And when you do a set ref on ampersand A and E, you transition to the setter for A with the argument E. Now there's no possibility of it going wrong. So this is why it's typically done this way, because the capabilities are too weak. The type of the capability is not strong enough to enforce the invariant you want. So I use abstract types, of course, to enforce the invariant I want. So many popular languages, like all of them, don't have abstract types. They instead have some ooga booga about objects and encapsulation and some other nonsense. They don't give you abstract types. Okay, it's really annoying because it doesn't let you enforce the invariant. So that's an example of using abstract types to enforce a critical invariant, which is that the getter and the setter go together. Okay, next thing. So now I'll talk about, are you with me? Make sense? Okay, so the interesting thing is this makes perfect sense in the context of scoped assignables. There is nothing about it, okay, that breaks the so-called stack discipline, the fact that you can have these allocated in a stack-like manner. That is, you increase it and then down below the line you pop it back off. You know, you can have references, there's no problem. Okay? The whole setup with mobility and stuff makes that be the case. Now let's look at something else. So the move I made to define scoped assignables, the critical thing was to define mobility. When is tau mobile? That's critical. And we restricted, this was a restricted notion. Like, Nat was mobile under the understanding that it's eager, etc. You can write down the rules for that, it's restricted. But there's another move. If I get back over here and I find myself into trouble, there's another way out of trouble, which is to give up on the stack discipline. Okay? So what I do is I have something called MA with free assignables. Free assignables, that's short for scope free. I call them free assignables or scope free assignables. Okay? And what is the move? All types are mobile. So I decide, no, look, and I have to admit that's true. Okay, for all of Algol's virtues, having only scoped assignables is pretty damn weak. For example, you can't implement a mutable linked list. Okay, you can't have something in memory where the assignables are in memory and then you can pass them around and so on and get out of their scope. That's impossible. Okay, so that's a weakness of Algol. Okay. Modernized Algol doesn't have that weakness because I equip it with full PCF and everything works smoothly. But I still want to say, although Algol in some way is a baby language as it originally defined, it grew up into being a fully fledged adult. So that's the thing I want to get across here. Okay, so what you do is you say, all right, I don't want any of that nonsense. I want to make all types mobile. All right, so what do? So my move here was I defined a statics. I defined a dynamics that captured the scoping. Then I found myself into trouble, so I fixed the statics. That's what I did. But there's a whole other way to do this. You can just say, let's change the statics, make every type mobile. Now you better make your dynamics fit that. Okay? So how do I do that? Well, the dynamics now look like this. I write it like this. I have funny punctuation marks. And the reason is that everything I'm doing eventually connects up with process calculus and concurrency. So just bear with my idiosyncratic punctuation marks. So the new is a punctuation mark. Don't worry about it. So I have sigma, mu, m, makes an unlabeled transition to sigma prime, mu prime, and m prime. Okay? And the idea is this. The crucial idea is how I deal with declare. Okay? The way I deal with declare is I have the following setup. Where E is a value in sigma, I'm cutting to the critical rule. So instead of going above the line like I did here before to implement the stack discipline, I say no, allocate this assignable forever in a way that's never deallocated. Well, it could be deallocated by some scanning and garbage collection. You can talk about that if you want. But really, for all practical semantic purposes, it's never deallocated. So what do? Is I go across instead of going above the line, I go across the transition and I allocate A. So this has to be, I have to know this type tau. So I allocate A, I extend the memory, and I just start running M. And then, of course, I continue from there. Okay? So the idea is that, and then when I get here, what happens when I get here is you just return, the sigma becomes different, so I'll write it out. I'll write out the return. So let me make some space here. So what does the return look like? Well, the idea is that if you get into a situation like this, and you say return E, and E is a value, then that's just the final state. So the idea is that this guy can go along and it can compute whatever it likes, and it can start, it could return something that involves A. Who cares? Because it's already there. It never goes out of scope. Okay? So this is called the scope-free dynamics. So this is scope-free dynamics. If you like to say it, it's the assignables are heap allocated. I just throw them, extend the memory. Here's what the locations are. Give me a new location. Extend the memory, and then carry on from there, and it never goes away. So it's never deallocated. And now you can prove a safety theorem for that. And if you do that, then you can start programming, okay? You can start programming in very familiar ways, like you might do in C or something like that, because I have assignables and they're in memory, and I can put them in data structures, and I can form tuples of them, and I can make recursive types that involve them, and have mutable linked lists, and blah, 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 and do everything you want. Okay? Completely general, and it's completely type safe. Okay? So that's the idea. So that's called algol with free assignables. So what we see is, as it happens, no one anymore, and I understand why, nobody anymore buys into the idea you should have only scoped assignables. Okay, I get that. That's fine. Everybody works with free assignables, and then they rely on storage management to, collect up garbage. All right, and you can talk in the operational. By the way, everything you need to know about garbage collection can be written down in operational semantics in a completely clean way. Okay. All right, very clean. You can prove theorems about it and everything. Beautiful. Okay, very nice. So you can talk about that in this setting, and then that's what you have. So that's the language you have. And this language that I have, which is PCF, let's say I do the following thing. Let's say, okay, I started out with PCF. So let's say instead I do FPC, which is a generalization of PCF, as Dan was explaining to you yesterday. And I add into it the level of commands. So I really have a jazzed up algol. Then what do I have? Haskell. The fact of it is it has nothing to do with monads or premonads, nothing. Yes, the commands can be structured into forming a monad, yawn, so can lists and every other thing, okay? That's not the issue. The issue is that you have state and you introduce state, that's the command level, okay? And you have recursive types. Algol certainly didn't have anything like that, that's for sure. Neither did PCF. But if you had recursive types, that's what FBC is all about. That's basically what you're talking about, okay? The ideas were already present. Yes?
In the scope-free dynamics.
What's that?
In the scope-free dynamics, do we have to do some sort of assignable renaming event?
Yeah, thank you. That's a very astute. So, yes, I was glossing over that. This is bound within here, so I can always assume it's different from anything that's already in play, so that when I allocate it, it's fresh. Okay, so that's how I deal with that. Okay, and in this setting, what I mean is commands with free assignables, by the way. And there you are. Okay, that's what's going on. So that's what I mean when I say Haskell is a dialect of Algol. Okay, it's just a modern, I would call it the modernized Algol. Okay, because I just did PCF with commands, and you can also do FPC with commands. There's no problem with doing that. Okay, so let me just go through to make sure I've said the things I want to say. Yeah. So there's a lot of good exercises. Let me just check. I talk about capabilities, scope assignables. Let me just make sure I hit my points. For fun, okay, good. Yeah, there's the last thing I want to say. Good. Okay, for fun, there are exercises in the book that tell you how the notion of objects got invented in the context of Algol. So Simula 67, 1967, they jazzed up Algol in a certain way by allowing procedures to have a bunch of procedures to share some local state. That's just declaring some things and having procedures that are in the scope of that. That's no problem. And then the idea that you could have multiple instances of such a scenario. And that was called Simula 67. Okay, so that's where those ideas come from. And in the book, I have exercises that say, carry that out, it's fun. You can do it in the context of modernized Algol, and you can see what's involved. And you just say, oh, okay. So the idea is if you have the right type structure around, lots of things you can just peel off as programming. Okay, just writing programming. They're not fundamental in a certain way. Okay, so that's that. That's what I mean there. So the last thing I want to mention is this. Is what I want to do is to say I want to talk about at a high level. I'm not going to go through any code. You're all hungry and we're running a little late, so let me do this. So here is the big issue. And I must say, as far as I know, there's no good answer to this question. Okay? On Monday, Wednesday, and Friday, I feel a certain way, and on Tuesday, Thursday, Saturday, I feel the other way. So here's what I want to say. And the big issue is the notion of benign effects. So the situation we have here with Algol, which was, as I say, present in 1960. The situation we have here, is it still on the board? I guess not. Okay. The situation we have here, that's gotten erased. The situation we have here is we have the distinction between expressions and commands. And neither the twain shall meet. They are completely separated. The expressions are completely pure. The commands are so to say, completely impure. And that's it. They're completely segregated by the lax modality. Okay? This has many advantages. Okay? Because everything up here is just pure functional programming. In particular, when Dan talks about parallelism, there's no issue in putting in parallelism into the language. Nothing. You don't get involved in concurrency. It's great. Okay? There is an issue about what constitutes an effect. So, for example, exceptions are a very problematic thing, but I don't have time to talk about that. That's another mess if you have laziness, okay? But let's forget about that for the time being. Let's just look at storage effects, okay? So for storage effects, there's a lot of people who advocate strongly to make a separation between them, as did Algol. And it's good, okay, it's good. On Monday and Wednesday and Friday, I like this. I want to have parallelism. I don't want to get involved in concurrency. I like to have this thing. It's a very nice thing. On Tuesday, Thursday and Saturday, I join the real world, okay? And in the real world, the central notion that is problematic and that I don't know how to solve at the moment in a clean way, that at this moment I don't know how to solve, is how do you account for benign effects? You see, in a certain sense, if you see what I mean, you cannot implement Haskell in Haskell because the so-called pure level is extremely stateful because of the memoization. Oh, this really stinks, okay? So supposedly effects are terrible at the expression level, except that you use them at a blistering rate, okay? Why? They're an example of benign effects. So the very idea of laziness or memoization is a benign effect. What do I mean by a benign effect? You get purely functional behavior, but you get the benefits of call by need. What is the benefit? Efficiency. That once you evaluated something, you latch its value and you don't have to evaluate it again. It's about efficiency, okay? The way you get efficiency is with benign effects. I'm sorry, but that's the truth, okay? So look at things like splay trees or other self-adjusting data structures. Forget it. You can't do it. Oh, if you have your sacred separation between expressions and commands, well, you can forget about doing splay trees, any kind of self-adjusting data structure. Your Linux kernel has splay trees in it to do the page table management. Okay? It works using splay trees. Okay? So these things are serious. It goes on. There's endless examples. Endless examples. I'm currently working on version data structures. Okay, which again, it's a fundamental technique for getting efficient code. The point is, if you're serious, and even Haskell is serious in this respect, you must have benign effects. So it's a very bizarre situation to be condemning benign effects when you in fact rely on them for your life, okay? When you cannot have them at all, okay? It's all about efficiency. And this is goes back to an essay that Dijkstra wrote about 40 years ago. He called it On the Fact That the Atlantic Ocean Has Two Sides. And my paraphrase of this is, in Europe, nobody gives a damn about efficiency, and in the US, efficiency is of very paramount importance. You can draw whatever conclusions you like from that, but you'll notice, where is the software industry based in the world? It matters, okay? It matters. It's not like, oh, we just sweep that away. We don't care about efficiency. We do care about efficiency. So the hard problem that remains is that if you have a language like Algol or a derivative of Algol, it has lots and lots of good properties, which I love on some days. But you have to somehow figure out how to make that work so that you can get efficient algorithms in that setting. This you cannot do, okay? Okay, yeah.
Could I implement splay trees using free references?
Yes, using free references, that's exactly what you do. Okay, yeah. So that's the whole idea. But if you have I see what you're saying. No, but they will not be, no, I'm sorry, I misunderstood your question. The answer is yes, but then everything is a command. Okay, you no longer have a splay tree as a value. Okay, so you cannot get, so there's a conflict, okay, there's a conflict with persistence. That's the other issue, is persistence, is that in the pure language level, data structures have multiple futures. That's essential to parallelism. I can take the same list and have a whole bunch of things work on that list, okay? If you start having mutation, then you have a big problem, okay? So I'm simply saying I don't have a definite statement to make here, other than this is a serious question that cannot be swept under the rug, okay? If you have the kind of separation, you cannot have like a tree data structure that you might use in expression level for doing parallel computation or something that has benign effects. In fact, paper I'm working on right now is doing this, and is exactly how to let it be absolutely pure, but nevertheless have benign effects. But you've got to be in a language like ML where benign effects are possible. Otherwise, you're out of the game. So it's all very nice, you know, to talk about these kind of properties at a sort of, you know, philosophical level, but I would call attention to the fact that you can't neglect efficiency. So Dan, in his next lecture, is going to be talking all about efficiency, and he's going to be talking about the definition of parallelism, which is defined entirely in terms of cost. And so that's an interesting thing in itself. So I just want to simply say efficiency matters, and it's not very clear. It's not very clear how to make everything that you want live together in a civilized way. So all right. So let me finish with that, and that's the end of my lectures in this summer school. So thank you very much for your attention. I appreciate it.
Clear that when you teach, you precisely know what to say, when to say, and how to say, in order to be as clear as possible. This is something that is